Greeting to Dr. Ang Tao Kyung. We are from Group 1. I'm the leader part, and this is my members, Desmond, Loy, Cheong, Kong, and Go. Today, we are going to present our group assignment 1 with title Necessary Condition of Routh-Hurwitz Stability Criterion and its special cases. So this is the table of content. The presentation will cover the introduction, problem statement, methodology, example problem, and solution, and lastly, the conclusion. So about the RH stability criterion, it is a useful tool for evaluating the stability of linear dynamical system, and it can be used without the need to compute the eigenvalue of their Jacobian matrix. The characteristic equation describes the relationships between the input and output of the system, and the stability of the system may be classified as either stable or unstable based on particular criteria and guidelines related to the Routh-Hurwitz criterion. And these two fellows is the founder of this stability criterion.
Hi, I'm CHEONG, the next presenter. So I'm going to present about Routh-Hurwitz stability criterion. And for the dynamical system to be stable, the roots of its characteristic equation must lie on the left-hand side of the plane, which means that the roots must lie on the negative real part. Solving a characteristic equation algebraically can become difficult when the order of the equation increases. So Routh-Hurwitz stability criterion is used to overcome this limitation. A system is stable if all the roots of the first column in the Routh array have the same sign. So in that case, the number of sign change in the first column will result in the same number of roots in right-hand side of the plane. The next slide is the advantages and limitations of Routh-Hurwitz stability criterion. The advantages is the stability of the system can be determined without solving the characteristic equation. We also can avoid complicated steps in solving characteristic equation when the equation involves high order. And for some unknown in a characteristic equation, this criterion allows us to determine the range of the K so that the system is stable. Also, we can determine the point of intersection for root locus with an imaginary axis. However, there are some limitations. One of the limitations is only applicable to linear systems, and it also does not provide the exact location of the roots where it lies on the left-hand side of the plane. Also, the coefficients of the characteristic equation must be real in order to apply this criterion.
Hi, my name is Go. Now I would like to talk about the application of this Routh-Hurwitz. And for this, Routh-Hurwitz is often used to design and analyze in control system. The stability analysis is one of its main use. The criterion can offer a clear evaluation of system stability by looking at where the root of the characteristic equation that are located. The system is stable if all the coefficient of the fourth column of Routh array is positive or alternate sign. However, the system is regarded as unstable if the coefficient is 0 or changes in sign. System design make desirable use of Routh-Hurwitz criteria. The criterion is used to choose system characteristic that guarantee stability. It can establish the range of parameter value that the result in a stable system by modifying the coefficient of that characteristic equation. This is designing robust, dependable control system that adhere to the required performance criteria. Here is the problem statement. The Routh-Hurwitz stability criterion is introduced to compute the stability of a dynamical system with high-order characteristic equation. In this project, we are aimed to answer the following questions. First is, what is the necessary condition for Routh-Hurwitz stability criterion? For the second is, how to construct the Routh array table. And third is, how to determine the stability of the system from Routh table.
Hello everyone, my name is JING and now I'm going to introduce about the methodology for Routh-Hurwitz criterion. So suppose that we have a continuous dynamical system described by the differential equation x dot equals to fx, where x is in the Euclidean real space. So the Jacobian matrix for this system can be obtained as by using the formula as shown in the slide, and using the by computing the determinant of j minus xi equals to 0, we can obtain the characteristic equation, which is then reduced to a polynomial equation with n order defined as ps equals to cns to the power of n plus cn minus 1 s to the power of n minus 1 plus cn minus 2s to the power of n minus 2 plus dot 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 plus c1 s to the power of 1 plus c not equals to 0. Hence, the necessary condition for the Routh-Hurwitz stability criterion, the first is all the coefficients must have the same sign, and the second condition is that the coefficient must be non-zero. In other words, we can say that the system is unstable if there is at least one coefficient that has a different sign or is equal to 0. However, the necessary conditions are not sufficient for us to conclude the system stability. Hence, to determine the stability of the system, all the roots of the characteristic equation must have a negative real part. In other words, we can say that all the roots must lie in the stable left half plane of the complex plane, which can be observed by examining the sign changes in the first column of the Routh table.
Greeting everyone, my name is YIING. So now I will explain on the Routh table construction. So suppose we are given the polynomial equation PS as shown in the slide. So the first step, we need to verify the necessary condition for Routh-Hurwitz stability. So the necessary conditions are all the coefficients must have the same sign and also must be non-zero. And then to construct the Routh table, we need to arrange all the coefficients in the first two rows of the table, start from Cn to C0 by column as shown in the table, and then fill the remaining row using formula shown in the table. And then we continue until the first column element of S power 0 is H1. So these are the example of the general form of the Routh table. So the third step is to verify the sufficient condition for Routh-Hurwitz stability. So if there is no sign change in the element of the first column of Routh table, the system is stable. So if there is sign change in the element of the first column of the Routh table, so the number of sign change equal to the number of roots that exist in the right half plane, and hence the system is unstable. Next, there are several special cases for Routh table. So the first one is the first element of any row of Routh array is 0. So for this case, we just need to replace the 0 with a small positive number denoted as epsilon, and then continue computing the Routh table until the end. And then we need to determine the number of sign change in the first column of the Routh table by substituting epsilon tends to 0. And then the second case is all the elements of any row of Routh array are 0. So for this case, it is necessary to construct the auxiliary polynomial by using the coefficient from the previous row. And then we follow by the differentiation of that auxiliary polynomial, and we replace the row of 0 with these coefficients.
Hi everyone, I am DESMOND CHING. Then we move on to the example problem. Next slide. We consider that the special case of the round array, which correspond to the auxiliary equations SQS as shown in the slide. And we construct the row tables, but we found that there is row of the zeros in the S1 prevent the S-ray from being finished. And the part of the root of the characteristic equations are positioned on the imaginary axis. Next slide. And we have the equation that contain the coefficient from the arrest row and show that the Q auxiliary is equal to the 21 S squared plus the 63. And we have the system pole on the imaginary axis described by the root of the auxiliary shown in the slide. And we have the derivative of the Q auxiliary is equal to the 42S. And then we have the original of wrong array is changed to the change in the S0 is shown in the slide. Next slide. Next.
Yeah, okay.
Then we get the full X-ray as follow in shown in the slide. Then we notice that in the full X-ray, we have the two signs change, which show that one is changed to the -20 and the -20 is changed to the 21. Then we can conclude that there have the two unstable pole on the real part plane. Then for the system is unstable. Then we can say that the auxiliary equation is a important idea to identify the reliable proposition gain range that may be employed in the closed-loop system without work.
Okay, so I will conclude our project. So for a dynamical system to be stable, all the coefficients of the character equation must have the same sign and non-zero. And then the root array is constructed, and the stability is determined based on the sign change in the first column. So the system is stable if only if there is no sign change in the first column. So overall, the Routh-Hurwitz stability criterion is a powerful tool in the dynamical analysis, which overcome limitations such as difficult characteristic equations due to high order of existence of unknown constant. So this is our reference, and thank you for watching our presentation.